Hello friends, in this session we will be discussing about distribution of windings. Let's begin. See here, in step 1 if you see, in step 1 what we discussed, in step 1 means, see here, we know that E conductor, EMF induced in a conductor which is there is going to be proportional to flux density. Already we know that, right? Means, so our step 1, if you think of, our step 1 was what? To make this field flux as sinusoid as possible in space, right? So for that, what we did, we had a structure of cylindrical rotor, right? And then we spoke about salient rotor. But what happened was, in case of cylindrical rotor, we got stepped sinusoid. Already we discussed, we got stepped sinusoid. And in case of salient rotor, we got what? Peaky sinusoid. So what I am asking you is, are both of these sinusoid? No. They are going to be stepped sinusoid and peaky sinusoid. Means they are basically non-sinusoid only. Getting my point, right? They are going to be non-sinusoid only. Now, see here, very important thing. The moment these are non-sinusoids, but we have done some or the other arrangements here. We came to know that in case of cylindrical rotor, if we increase slots per pole, we can have the stepped sinusoid, right? And here if you think of, if we have eccentric structure, ECC, eccentric structure, if we have, then we will have this kind of waveform. Already we have seen that, because rather than having this flat topped flux distribution in space, it is better to have stepped wave and better to have peaky sinusoid. That is what we have understood. But we need to understand one thing, that these are going to be non-sinusoid. Moral of the story, we have tried our level best to make flux sinusoid, but it was impossible to make the flux sinusoid. But we tried our best, level best, right? So if we think of here, see here, so step 1 is over, step 1 is done. What is step 2 then? Now we will try to make induced voltage sinusoid. Let us see if we can get induced voltage sinusoid. So make step 2, make induced EMF sinusoid. Right? Yes, if you say here now, this one, E conductor proportional to B, because see, you please tell me one thing, if my, flux, if my flux with respect to space, if it is stepped wave, then 100% EMF induced will also be stepped wave. Why? Because they are proportional. If my flux is going to be peaky sinusoid, this is also going to be same. Moral of the story, whatever way my flux will be, the same way induced EMF will be there in time. This flux distribution will be in space, and the same representation, the same induced voltage here will be also there here with respect to time. Already we know. But what is important for us now, here we will be doing two things in step 2. Number 1 is, we will be doing distribution of winding. And another thing which we are going to do is going to be short pitching. Why? In order to make induced EMF more sinusoid. I am not saying that exactly sinusoid, but more sinusoid we can make. Let us talk about distribution of winding first, and then we will speak about short pitching. We will be doing two things from now. Number one is going to be analysis, and number two we are going to do is nothing but formulation of equations. Formulation of equations. Yes. So now in analysis we will be having some different flux poles, and in case of equation we will have some different poles. How we will have, let us see. See here, this is going to be, let us say, south pole of the field, and this is going to be, let us say, north pole of the field. This is going to be rotor, right? Already we know because it is the shaft here shown by red. Anyways, so now from now onwards, for example, this is salient. So from now onwards, if I think of, I will have no difference between these two. I will see no difference between these two. Why? Because even if it is cylindrical or if it is salient, harmonics are going to be there. What are harmonics? We will talk. Don't worry about it. But see here, because we have already seen that in case of cylindrical also I am going to have stepped sinusoid, which is a non-sinusoid, which means even here also I am going to have some of the other harmonics. And similarly in case of salient also I am going to have some harmonics because it is again non-sinusoid, or we can say peaky sinusoid. So what I am going to do from now, I don't care whether it is cylindrical rotor or it is this one. Why? Because my intention is now, my focus is now where? Armature. My focus is on armature induced voltage. That is the reason I don't care now whether it is salient rotor or this rotor. I don't care. Number one point. Number two point is what? Whenever I am writing SF and NF, which means it is going to be along with harmonics, or we can say poles along with harmonics. Right? So whenever I am saying F, SF, NF, which means it is going to be what? Poles along with the harmonics. Whereas, see here. First of all, both of these are same for me. Why? Because right now I am focusing on what? Armature induced voltage. So I don't care whether it is salient or this, it's okay. I have no problem. Second thing, what I am going to do is, let us think of harmonics. If for example this is flux density, or we can say MMF also for time being. So, and this is going to be space angle alpha. This is with respect to space angle alpha. Space angle in the sense mechanical. See here, space angle in the sense, for example, if I cut this like this and open it in the sense, this is 0 degrees, this is going to be 180 degrees, this is, and then again 0, 90, 180, 270, and then again back to 360, that way, right? So that is what in space, if we think of. So in space, if we see distribution of this B, for example, if it is, let us say, this way, for example, then this is stepped cylindrical rotor, right? So here what will I have is, see here, what will I have? This is nothing but flux distribution with space angle. Here I will have some fundamental component here, this way, right? This is going to be fundamental component. What do you mean by fundamental component? Fundamental component in the sense, see here, this particular red which is there, what is the frequency? Same as non-sinusoid or not? Means, see here, for this particular portion for this one cycle, for this one cycle, if you think of, for this one cycle, if my non-sinusoid is traveling one wave, or if my non-sinusoid is completing one cycle, then this particular fundamental is also going to complete one cycle only. Hence, it is called as fundamental. Let me write this as fundamental. Now, see here. See here. For example, now I may have this way. So, in the same time, if you see what is going to happen, this is one cycle, two cycle, three cycle. So, this is called a third harmonic. Now, see here what is harmonic. See here. There was a scientist named Fourier. What did Fourier say? He said that whenever you have a repetitive or periodic non-sinusoid, it can be represented as a sum of so Fourier said that whenever you have repetitive or periodic non-sinusoid, it can be represented as a sum of different frequency sinusoids, which means, see here, if you think of this particular red, this red, if you think of, red is what? Red is going to be fundamental. What about green, if you think of? Green is going to be third harmonic. Why? Because when this one wave, red, fundamental, if you think of, when it is going to complete one cycle, when my fundamental completes one cycle, my third harmonic completes 1, 2, 3 cycles. For example, I may have some fourth harmonic, let us say, fourth harmonic in the sense 1, whatever it is, maybe seventh harmonic or fifth harmonic or something. Let us say it is fifth harmonic, for example. Or I can have some even harmonics also, means this is going to be even harmonic, this one, or we can say second harmonic in this case. Number 2 is even, right? Now see here, if I add red, green, yellow, red, what do I get? I'll get the blue, which is non-sinusoid. Again, if I add this particular red, which is what? Fundamental component, with third harmonic component, with second harmonic component, with fourth harmonic, with fifth harmonic, with sixth harmonic, with 10th harmonic, 20 harmonic, 100 harmonic, 1000 harmonic, some harmonic here like this, all the harmonics, then what is going to happen? It is going to give me what? It is going to give me this non-sinusoidal blue waveform. That is who said this? This was said by Mr. Fourier. Now, for analysis purpose, see, for analysis purpose, I will be considering non-sinusoid only. Non-sinusoid in the sense this, SF and NF. SF and NF is what? Sum of fundamental plus harmonics. Getting my point, right? this SF and NF will be what? Sum of fundamental and harmonics. Whereas in order to have equations, there is something called as KD, KP and all. We will see that. What it is, time comes, I'll tell you. But in order to find those equations, we will be taking some other things. For that, for formulating equations, what are we going to use? See here. For equation purpose, if you think of, earlier for analysis purpose, I will be considering SF and NF. But now here I will be considering S1 and N1. What is S1 and N1, sir? Fundamental. Fundamental component, meaning that S1 and N1. Meaning that, see dear, see here. Meaning that this red. Meaning that, see here, this particular blue which is there, blue, non-sinusoid, that will be used for analysis in terms of SF and NF. SF and NF will be representing this blue. Whereas my red, where is that? This one. Whereas my red, fundamental component, right? This red which was there, this is my fundamental component. This I will be using in order to have equations. So see here, why I am going to use this one only for equations, I will tell you why. But for time being, just understand one thing, that for analysis purpose, while analyzing thing, I will be using SF and NF, which will be nothing but non-sinusoids. SF and NFs are going to be non-sinusoids. Whereas for analysis purpose, I will be taking sinusoidal flux densities. In the sense, I will have N1, S1. 1 indicates what? Fundamental frequency. 2 means what? Second harmonic. 3rd means third harmonic. See here, this way. So this is going to be fundamental. Then next, I may also think of as S2 and N2. S2 and N2 is what? Second harmonic. This is all happening in space. Field flux happening in space. Anyway, see here. If I think of here, what is going to happen? This is S2 and N2. So I can consider S2 and N2. Whether it is cylindrical or this one, it does not matter to me. Why? Because my focus is on induced EMF, that is on armature. So it will be fine. This is what we will be trying to do. I may take, N3, S3 as well. When time comes, I may take N5, S5 as well. It's okay. That will be nothing but the harmonic poles, right? Anyway, see here. One last time I'm going to explain this. See, blue, non-sinusoid, that can be represented as sum of fundamental and harmonic components. So for analysis purpose, I will be taking blue, non-sinusoid, and in order to get the equations Kp, Kd and all, what will I do? I will use fundamental component or harmonic components. Means for those equation purpose, I will write N1 and S1 And for analysis purpose, from just now, if I think of, I will only use NF and SF. And for equation purpose, I will be using N1 and S1. I hope things are clear. Anyways, next. Let us think of a stator like this. This is going to be a stator. Now, let me consider 8 conductors. Let me call this as 1, conductor 1, conductor 2, conductor 3, conductor 4, conductor 5, 6, 7, and this is going to be conductor A. Now see here, very simple, very simple. Let me consider a rotor here. Right? Now let us have this one as NF, because yes, already we thought of that this particular NF, whether it is salient, cylindrical, doesn't matter to us. Why? Because our focus will be now on armature. Anyways, this is going to be NF and SF, for example, and let me rotate it in this direction. Let us say omega. In anti-clockwise direction, let us say I am rotating it. Now this is very important thing. See here. Yes, see here. Now what I am supposed to do, for example, see here. If this is NF and this is SF, right? Here I am going to do a small mistake, but it's okay, no problem. I'll tell you that. See here, this is NF and this is SF, right? So flux is going to be upwards. Flux is going to be this way. What is the direction of my conductor? Conductor will move in that direction. Why? Because see here, flux is like this, upwards, out, right? Upwards it is. Now, what do you think of this? Now this flux is rotating in this direction, right? This is flux. Flux is rotating in this direction, which means what? See here. This is my flux, upward flux. Poles are rotating in this direction, which means with respect to my poles, conductor is moving in this direction, which means conductor rotation is in this direction, left to right. This means induced emf is going to be middle finger, which is going to be dot. Dot here, and this is going to be cross here. Right? 100%. Now see here. Let me erase this. Let me draw phasor diagram here. Let me draw phasor diagram for this. Now see, we know that here, if you have studied somewhere, basics and all, you may know that whenever we talk about phasor diagram, see here, first of all, let us understand, this is NF and SF, which means it is what? Non-sinusoid, which means EMF induced will also be how? Non-sinusoid only. Why? Because E conductor is proportional to flux density. That is what we know. So if flux density is, for example, here it is NF and SF, which means it is having harmonics also, which means it is non-sinusoid, which means EMF induced will also be what? Non-sinusoid. Getting my point right? So if it is non-sinusoid, can I represent it in terms of a phasor diagram? Can I represent non-sinusoidal waveforms in a phasor diagram? Answer is no. In order to represent anything in terms of a phasor diagram, what you need? Number one thing, you need that all phasors represent sinusoids. Rule number one is what? All phasors should represent sinusoids. I may teach you transformer and all. That time I will discuss about it as to why it is so. Right now, let's not waste time. Right now, you just remember one thing, that all phasors represent sinusoids only. That's it. Work is done. Anyways, see here. If I think of this one, so You will say, sir, but you have taken NF and SF, which means they are having harmonics also, which means it is non-sinusoid. And now you are saying that no, you have to take all phasors represent what? Sinusoids. Which means I cannot use NF and SF. Rather, I should use N1 and S1 here in order to get the phasor diagram. This is what we need to understand in order to get the phasor diagram, and from here only equations and all will come afterwards. So I cannot take here SF and NF. Here I have to take N1 and S1. Why? 1 represents what? Fundamental. Anyway, see here. Let us think of phasor diagram. See. Now this is very important. Focus. Let me consider mobile torch. Mobile torch now. Let us have mobile torch here. You just on the torch from here. What is going to happen? Light rays will come this way. Light rays will come this way, right? These are going to be light waves. Now, the moment you have these light waves, what is going to happen? And let me consider a plane here. Let me consider a plane here on which you will have the reflections. Yes. Let me consider a plane here on which you will have the reflections of the same. Right. See here. Concept is very easy. Just focus. See. We know that second rule. All phasors rotate in anti-clockwise direction always. Why in anti-clockwise direction only? Ancestors said so. That is the reason we are going to think of it as anti-clockwise direction. Anyway, see here, very easy. Very easy, see here, very simple. Which means now, for example, I have phasor. This is, for example, the phasor, right? And this phasor is rotating this way, in anti-clockwise direction. Moral of the story, this particular phasor will, at the end, rotate in what direction? Anti-clockwise direction only, and it will form a circle. So let me have a circle here. I am going to have a circle, and my direction of rotation of the phasors is going to be this way. Anyway, see here. Now you please tell me what will be even. Even, what will be induced EMF in this conductor, first conductor? It is going to be even. So you please tell me, even here, is it dot? Yes, it is dot, which means it is going to be positive maximum. So even is going to be, this is the center of the cell, this is going to be even, and it is going to be positive maximum, right? So if even is positive maximum, at the same time, if you think of when rotor is here itself, when my rotor is here, N1, S1, at the same time, think of 5. Here, what you have? You have cross here, which means opposite to first conductor, which means it is going to be E5. Getting my point, right? So now I have got E1 and E5. Now see here, focus, very easy, see here. Now, you please tell me, what about E2 and E8? You will say, sir, if E1 and E5 are this way, let us take E2 here and E8 here, right? One was here at the top, we took here E1. 5 was here, we took it here, 5, E5. But what about E2 and E8? E2 and E8 also, you may say, sir, yes, E2 and E8 also, we will take 2 here and 8 here. Let us analyze. Can we take them that way? Let us see. See here, very simple. Roughly, if you think of what is the angle between them, this and this one, what is the angle? And this one. Roughly, this angle is going to be 45 degrees. And this angle is also same, 45 degrees. Now see here. When my field was here, E1 was maximum, right? Now, The moment this one, now see here, if this n1 is rotated here, if this n1 is rotated here, s1 comes here, what is going to happen? What is going to happen? Just think. If this n1 comes here, s1 comes here, means after 45 degrees, after rotation of 45 degrees, what is going to happen? After rotation of 45 degrees in space, what is going to happen? Here I will have maximum induced EMF in it, and here also I will have maximum induced negative voltage in 4, which means, see here, when this one E1, when this E1, if you see here, when this E1, if it is rotated by 45 degrees, if for example this complete thing, complete phasors, right, at initial stage when N1 is here, S1 is here, E1 is maximum, E5 is negative maximum. Now after 45 degrees, what is going to happen? After 45 degrees, what is going to happen? After 45 degrees, this will also rotate by the same angle. Why? Because space and time are synchronized. Already we have discussed from space to time to space and concepts and all, right? So since time and space are synchronized, what we can say that when this one is rotated by 45 degrees, my phasors in time should also rotate by 45 degrees. These are all time, right? Why time? Because it is nothing but voltage. Voltage is always time displaced. Already we know that. Anyways, see here. Very simple. Focus. Once and for all. See here. Initially, N1 was here, S1 was here. When N1 was here, S1 was here, E1 was positive maximum. So, when N1 was here, S1 was, E1 was positive maximum. When this, what do you say, this field poles, when these poles rotated by 45 degrees, what happened? When these poles rotated by 45 degrees, what happened here? 8 became maximum, means after 45 degrees, means after rotation, what is going to happen? When this particular phasor, when this E1 will get rotated by 45 degrees, this phasor will come here and it will become maximum. I hope you are understanding the point. Again, see here. Initially, N1, S1, E1, E5 maximum, no problem. After 45 degrees, what happened there? After 45 degrees, this N1 will come here and S1 will come here. So, after 45 degrees in space, what is going to happen? E8 will become maximum, right? After 45 degrees. So, now just think, if this particular phasor E1, if it is rotated by 45 degrees now, if it is rotated by 45 degrees now, which means this particular phasor will become maximum. So from there we understand that after 45 degrees, 8 is going to be maximum. E8 maximum will be there. So similarly, after 45 degrees, when E1 will come here, this will come here and it will become maximum. See here, after 45 degrees, when E1 comes here, this particular phasor will come here, which means this has to be E8. I hope you are understanding my point. Means after 45 degrees, E8 will be maximum, which means here also after 45 degrees, E1 will come here and this E8 will come here, which means this has to be E8 only. This has to be E8 only. Now, see here. The moment it is going to be E8, opposite to that is going to be what? What is there opposite to that? E8, 4, E4. So here E4 is going to be there. Similarly, if it is E8, if this E8 is shown there, which means E2 will be where? E2 will be here only. Why? Let us analyze one last time for E2. See here. This E2 which is there, when this one, for example, in history, if you see, this N1 was here, right? In history, if you see, first case was what? N1, S1 is like this. In history, N1 and S1 were like this. So in history, if N1 and S1 were like this, it means that in history, E2 was maximum, means 45 degrees in past, before time, E2 was maximum, which means what is going to happen when this E1 is there right now, before E1 if you see, E2 would have been here in place of E1, which means E2 was maximum initially. See, very simple. See here. Let me consider the poles now at N1 and S1. If I think of they are at this and this is, let us say this is N1 and this is going to be S1, for example. The moment this N1 is shifted here, S1 is shifted here. Now see, what I'm saying is I'm talking about history. See, when N1 and S1 are here, they are rotating in this direction, which means initially they were here as well, no? Somewhere in history they were in here as well. After that they came here, after that they came here, after that they came here. Getting my point, right? So see here, in the history E2 was maximum. So in the history means 45 degrees before. Right now E1 is maximum. 45 degrees before, if I see, before rotation of this E1 means E1 was here 45 degrees back, which means E2 was here, which means E2 was maximum. I hope you are understanding the point. Anyways, this is E4. If this is E2, this is going to be what? E2. Opposite to E2 is going to be E6. Right? And here also, what is going to be there? If here we have E7, means E7 will come here now towards the right, and here is going to be E3. I hope you are understanding the point. Now see here. Let me show the same. Now see here. You may ask me, sir, but if you see, for example, when this was there, when this N1 was here, S1 was here, 1 was positive maximum, E1 was positive maximum, but at the same time E2 was going to be what? Less than positive maximum. Why? Because it is under the influence of the same pole, right? So when first conductor E1, when E1 was positive maximum, this E2 and E8 were what? Less than positive maximum or not? Less than positive maximum. So then why do you take all the lengths of the phasor same? By the way, let me tell you one more rule of phasor. One more rule of phasor is what? One more rule of phasor is what? This was second one, this is third. What? Length of phasor. Indicate RMS or peak values. Right, RMS or peak values. So if you think of this peak and this peak, these are not at peak, right? At the same time, yes, they are not at peak, it's okay. See, these are phasors. If you know the basics of phasor, you must have known that this is nothing but the phasor. We are using this horizontal, reflection here. The moment we use horizontal reflection here, what we get here is on the plane is something like this. If I think of E1, E1 is this way, for example. This is going to be E1. So if I think of E1 is this. Now, what is the horizontal reflection of E1? Maximum. So here, E1 is going to be maximum. Now, what is the horizontal reflection of E8? E8 is going to be this much. Horizontal reflection is going to be this much only. So here, at the same time, E8 is going to be somewhere here. This is going to be E8. Right? And E7 at the same time is 0. Why? Because this is this way. So horizontal reflection of this horizontal line here will be 0. I hope you are understanding the point. Anyways, let's move forward. Let me erase this. See here. Yes. Now you please tell me, all of these things are inscribed in a circle or not? Yes, all of them are there. So can I represent the same? This is very important. Can I represent the same? Let me draw the same circle here. Now, can I represent the same thing here? Let us see. You please tell me. This is E7, right? This is E7, this horizontal. So let me have this horizontal here. let me say that this is going to be E7. Now E8 is what? Leading by 45 degrees. E8 is leading E7 by 45 degrees, which means E8 is this way. So let me draw this one here. So this is going to be E8. Right? Now E1. E1 is again 45 degrees. So this is going to be E1. Vertical E1. Now after that, see here. This is going to be E2. E2 is this way. So let me draw E2 this way. So this is going to be E2. Then if you think of E3, E3 is again horizontal this way. So this is going to be horizontal E3. Right? Now E3 is done. E4. E4 if you think of, E4 is this way. E4 is this way. E4 is this way. So let me draw E4 this way. This is going to be E4. Now once E4 is there, what is there next? E5. E5 is going to be straight downwards. So this is going to be E5. And what about E6 if you see E5? After E5 is going to be E6 this way. So this way I will show E6. So moral of the story, the same phasor diagram is shown here in terms of E1, E2, E3, E4 in this particular structure, and this particular structure is very useful in formulating the equations. How? I will tell you, don't worry. This particular thing is called as EMF polygon. This is called as, this one is very important. Now if you think of a stator like this, our stator like this, right? And let me consider conductors. Let us say this is A, then this is going to be B. A and A dash are going to be opposite. Should they be opposite? Let us decide. That decision will be taken by number of poles. Alright? Already we have discussed that, right? In case of two poles, if you think of A and A dash should be 180 degrees opposite to each other, and in case of four poles they have to be 90 degrees apart. Already we have seen that in, I guess, space to time or time to space, something like that. Anyways, see here. So this is going to be A and this is going to be A dash. This is B. This is going to be B dash. Then B dash. Then after B you have C here. This is going to be C, and here you are going to have C dash. Right? Now see here, very easy. This is, let us say, N1 and S1. N1, S1 or NF, SF, it's okay. Doesn't matter. What I am trying to say is, let me consider NF, SF only for time being. Now, we have to do one important observation here. What is your observation, sir? See. If you think of, this upper half portion is under the influence of North Pole, whereas this lower portion, if you think of lower half portion, it is under the influence of South Pole. Then see here flux density is going to be maximum. Here it will be reducing. Here it is going to be 0. Here it is going to be 0. Again, here it is going to be maximum. Here it is going to be 0. Increasing. It is going to be 0, depending on the flux distribution. But yes, 100% here it is interpolar axis. If you think of here, flux density has to be 0 only, or we can say MMF, which is here in this interpolar axis, has to be 0. Rest, whether it is going to be square, or it is going to be stepped, or it is going to be sinusoid, we don't know. We will analyze that. But right now what our observation is, see here. Our observation is, if you think of observations, what is the observation that you make out is that for one pole, if you see, for this particular pole NF, if you see, we have all the three phase conductors. Means, can I write that under each and every pole, if you see, for example, this is one pole NF. Under this NF, you have all the three phases related conductors, or I can say that you are going to have all the three phases related slots. This conductor have to be placed in slots, right? These conductors which are there, those conductors will be present in slots only. So what do we get here? We have understood that yes, there has to be slots. There has to be slots here. So I can say that under each pole, all three phase related slots should be present. Getting my point? Under each pole, all three phase slots or conductors, or we can say slots also, no problem, no, because at the end of the day, conductor will be present inside slot only. So all three phase related slots have to be present. Now these slots, whether they are this way or they are this way, we will discuss. Time will come, we will be talking about slots as well, about slot, harmonic and all, something like that. Anyways, I hope you have understood this. This is the first observation we have made from this. Now, here if you observe, I am going to have how many slots here? 1, 2, 3, 4, 5, 6. I am going to have 6 slots. Am I right? Now, what will happen if I have 18 slots? Let us see. Let me consider 18 slots. 18 slots in the sense, sir, see. This is going to be my stator, bullseye. Now, the same thing. Let me repeat the same thing. This is going to be A slot, A dash slot. This is going to be B slot, B dash slot. This is going to be C slot and C dash slot. The moment I am keeping A and A dash 180 degrees apart, which means it has to be two pole. Now yes, whether this particular rotor is salient or any rotor, it does not matter to me. It does not matter to me. Why? Because my focus is on armature. Anyways, let me consider this as NF and SF, let us say. Right? Now, see here. If you think of this A, B dash, C dash and all, right? Now, if I have 18 slots, rather than these 6 slots, if I have 18 slots, what does that mean? What does that mean? That means that I will have 2 more conductors here. Means I will have here A1, this is going to be now A2 and this is going to be now A3. For 1, if you see, I will have 3. Similarly, I am going to have 3 here. Means I am going to have this. If this is A3, opposite to that, diametrically opposite to that, I am going to get A3 dash. If this is A2, opposite to that, I am going to get A2 dash. And if this is A1, opposite to that, I am going to get A1 dash. I hope you are understanding my point, right? Now, if for phase A now, for phase A, if I have these 6 slots, for phase A, one phase, I have got this 6 slot, right? 1, 2, 3, 4, 5, 6. So, for similarly, I will have for C also, C1, C2, C3. Similarly, I will have for this one B dash also, B1 dash, B2 dash, B3 dash. Similarly, I will have here also B1, B2, B3, and I will have C1 dash, C2 dash, and C3 dash also, respectively. Right? Now, what are the total number of slots? If you see, these are going to be 18 slots only. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 18 slots. So, the moment I have 18 slots here, what I did was, I distributed the winding like this. Means, Here comes a very important term. See here. If you think of this part here, in this one, I had only one conductor, one slot, or I can say that for one phase in the sense, out of the three phases, for one phase I had dedicated one slot. Now this particular one slot, if you see, this was under one pole and it was of one phase. Very simple. See here, these are going to be the total number of slots. How much are they? 6. Now if I try to find what are the slots dedicated for one phase, how much will be there? Very simple. Total number of slots per pole, if you see, half is going to come. Per phase, if you see, one slot you get, right? See here, see again. One rule was what? Under each and every pole there has to be 3 phase related slots, right? So now if you see here, under one pole, if I consider this as one pole, for example, this is, by the way, rotor shaft. This is going to be, for example, one pole. If I see, then under this one pole, all the 3 phases are there or not? Yes, all the 3 phases are there. Now how many slots are dedicated for distribution of winding? How many number of slots are dedicated for distribution of winding? Means, see here, when I had 18 slots here, when I had 18 slots here, when I had 18 slots here, 3 slots were dedicated for one phase under one pole. This is called as, see here, initially a conductor was there, one single A conductor was there. Now that A conductor has been distributed in A1, A2 and A3. Now how many slots? How many slots? Means number of slots in which distribution of winding happens is given by, or we can say that number of slots available for distribution of winding. Number of slots available for distribution of winding is going to be given by Q, which is equal to slots per pole per phase. This is called as slots per pole per phase. What is that? Let us see. See here, very simple. Let me just compare these two so that you will get a clear idea. See, initially if you think of here, this was A. Now here if you see, you had 6 slots. Total slots were 6. Right. Now out of this 6 slots, half were for North Pole, half were for South Pole. So out of these 6, if you see, because we had 2 poles, so how many slots were there for each pole? 3 slots. Total slots were 6. Number of poles are 2. Right? 1 and 2. So how many slots were there per pole? 3. Right. Now we have understood that initially that under each pole, how many slots are there under one pole? 3. Now under each pole, I know that I should have all the 3 phases related slots. Means under each pole, see here, again, under each pole, this is one pole. Under this one pole, if you see, there can be 6 slots, 12 slots, 20 slots, 1000 slots, I don't care. What I am caring is, all these slots should be distributed with all the 3 phase related slots. Means, see here, again, very simple, see here. This is going to be, this upper half is going to be one pole, right? So just see here, total slots are 6, out of which how many slots are dedicated per pole? 3 slots per pole are there. Now we have understood that under each pole all the three phases has to be there, which means if I am having three slots here, which means in these three slots all the three phases should be present, which means slots per pole per phase. See, feel it. Slots pole per phase. So per phase, if you see, I am going to have here one slot per phase, one for A, one for B dash, one for C dash. Similarly, if you see here, see total slots per pole per phase. These many slots are available for distribution. Again. See here. Total slots. These are total slots. Feel it. Total slots per pole per phase. Again. Total slots. Right? This is circle. Total slots per pole per phase. So if you see here, if we see that slots per pole per phase will actually give me the slots, how many slots are dedicated for one phase under one fold for distribution. That is what is there. So number of slots available for distribution of winding is going to be Q is equal to slots per pole per phase. Yes, so now let us move on to analysis. Let us see. In order to do analysis, let me consider two cases. This is going to be, let us say, case 1. If you think of case 1. In case 1, what I am going to do is very simple. This is going to be the stator, and what I am going to do, let me have this here. Right? Now, see. And let me consider one rotor conductor here. This is rotor. Let me inject cross current here and dot current here. Right? The moment this is cross and this is dot, which means flux is going to be out of the rotor from here, which means this is going to be north pole of the rotor. Let me call it as north NF, because analysis we are doing. Analysis case, we are going to take harmonics also. This is going to be SF. Now, you please tell me one thing. How will be the flux distribution for this one? If you observe, this is what? One slot per pole. See here. Two slots are there and two poles are formed, which means one slot per pole. In that case, we know that we get a distribution of flux like this. And this distribution of flux is the worst distribution of flux. We have seen that previously. This is the worst distribution of flux. Anyways, let me consider now. Let me think of three slots, or we can say three conductors rather, like this. Let me say that this conductor is A1, the stator conductors, okay? A1, A1 dash, A2, A2 dash, A3, A3 dash. Why they are going to be opposite? Because two poles, we know that. Anyways, now let us think of that this is rotating in anti-clockwise direction like this. As usual, anti-clockwise direction. Now see here. What is going to be the flux distribution in space if you think of? Flux distribution in space. If you think of flux distribution in space, it is going to be this way. This is going to be B. And if it is varying with space angle alpha, then it is going to be like this. which is nothing but this only, right? Which is fine, no problem. This is going to be it. Now, by the way, when I am talking about A1, A2 and A3, these are the conductors of the same phase. These are not like, A, B and C. These are the conductors of same phase. Why? Because we have already seen what? Space to time. Space to time means in space, if my field is rotating by 120 degrees, then in time I should get time displaced induced EMF by 120 degrees. So there we have A, then we have B. Similarly here I can have B1, B2, B3, B4 here, B1, B2, B3 here, B1 dash, B2 dash, B3 dash here. Again I can have C1, C2, C3 here, and I can have this. But for time being, for simplicity, I am taking this particular structure. Anyway, see here, this is going to be the flux density with respect to space alpha. That is space angle. Don't worry about it. That is with respect to space only. With space, if you think of, this is the wave, and that is the wave shown there. Now, see here, we already know that E conductor is proportional to flux density, which means if my flux density is a square wave this way, then what will happen? Induced EMF will also be in the same way. So, let me think of induced EMF. Very easy and very important. Don't worry, this is very easy. This is going to be time, and this is going to be what? E conductor. E. Now, let me consider EA1 first. How will it be? EA1 will be also the same way. Because if my flux density is square, then EA1 has to be square only. Now, let me think of EA2. EA2 is where? EA2 is also here. EA2, see here, when this particular rotor is going to rotate in this direction, what will happen? This north pole NF will come here, SF will come here. The moment NF comes here, now see here, very easy. The moment NF comes here, and NF, which means it is going to be upwards. Let me consider this as when this NF comes here and this SF goes here. The same one, the same pole, this NF, when this NF travels from here to here, what is going to happen? When this NF tries to move from here to here, what is going to happen? Flux is going to be outward from the north pole. We know that. The moment flux is going to be outward. Now, since the flux is also rotating in this way, which means with respect to flux, my conductor is moving in this direction, which means I am going to get dot induced polarity current induced EMF here. Dot induced EMF here. The same dot induced EMF you are going to get here. Same you are going to get here. Right. So, if you just see here, what is going to happen? This is going to be the dot induced EMF. Now, if you think of E2, at the same time, when EA1 was maximum, at the same time only EA2 will also be maximum. And the same flux, see here, this is the MMF wave, right? This is nothing but flux, or we can say MMF wave. This is going to be that north and south. This is that MMF wave. Let me consider this one. This is the MMF wave like this. Now, what is going to happen here? For example, this is the wave, MMF wave. This is going to be the MMF wave like this. What is going to happen? After some time, this wave will come here. After some time, the wave will go there. After some time, it will go down. Getting my point, right? So, what do you understand from here? You understood that EA2 which is there, it will be also, because at the same time only, see, all of these A1, A2 and A3 are above each other, right? A1, A2, A3. So when this MMF came from here to here, what happened? A1, A2 and A3 got induced voltages at the same time. At the same time, in the sense, E2 will also be this only. Same value only. E2 will also be the same value. What about E3? What about E3? EA3? What about EA3? EA3 is also going to be this way. Right. Now, Now see here, if for example, this is A1 conductor, A1 dash conductor, A2 conductor, A2 dash conductor, A3 conductor and A3 dash conductor we know. Now if I somehow connect them in series, what is going to happen? What is going to happen means A1 here, see here, wire I will have A1 back to back connection, A1 dash, again A2 back to back connection, A2 dash, again A3 back to back connection, A3 dash. If I have it that way, series connection, what is going to happen? Voltage will be added or not in series? Voltage will be added, which means EA1, EA2 and EA3 will be added. So let me have this one green as E, what do you say, A1, A2 and A3. If all these three are in series, what is going to happen? I will going to get 1, 2, 3. This is going to be it. This is going to be my resultant voltage. Now this will be equal to what? Resultant voltage which is there, it is equal to what? It is nothing but EA1, A2, A3 which is equal to 3 times what sir? 3 times of EA1 or 3 times of EA2 or 3 times of EA3. Why? Because all are equal. How do you know that? Because same MMF wave. This was MMF wave, constant MMF wave. Constant MMF wave was there. This wave came here. Same wave came here and all of them were on the top of each other, right? Now that is the reason you have got this one. Now how much it is? Should we write EA1, EA2 or EA3? Better what we can do is, no, we will write EA1 is equal to EA2 is equal to EA3 and so it is equal to nothing but E conductor, let us say. This is equal to E conductor. So let me have EA1, EA2, EA3 to be equal to 3 times E conductor. I hope you are understanding my point. Now here, if you think of, see, what has happened? Because of this MMF, see, we cannot do anything with the MMF right now. Why? Because we are only going to focus on armature. Why? Because we are trying to make induced voltage as sinusoidal as possible. Now, let us think of case 2. Case 2 means what, sir? Let us see. Let me have stator here. And let me have rotor. Let me have this rotor. Now see here, this is going to be rotor conductors. Let me flow cross current through this and let me flow dot current through this. Right? Now see here, this is going to be cross, this is dot. So this is the way flux is going to be there. So flux is going to be out of the rotor from here, which means this is going to become north pole of the field, NF and SF. Why? Because we are considering it as non-sinusoidally we are considering, right? What? Non-sinusoidal means what? This one, flux distribution. Since this is cross and this dot, which means it is for what? One slot per pole. One slot per pole means this is going to become the flux distribution. And let me consider that I am rotating the rotor by omega speed in this direction. Now, let me have 3 conductors here, distributed conductors like this, which are distributed in slots this way. Initially, what I had, there were 3 conductors in one single slot, whereas here now I will have all the 3 conductors in 3 different slots. So this is again this way. So let me consider this as A1. If this is A1, then this has to be A1 dash, diametrically opposite to it, 180 degrees opposite, out of phase. Now this is, if this is A2, then center only A2 dash has to be there. Then if this is A3, then opposite to this A3 dash has to be there or not? 100%. Now if we think of flux distribution or MMF distribution in space, let us say this is B, or we can say MMF also, no problem, it's okay. We are saying MMF and flux to be proportional. Anyways, this is going to be, let us say, with respect to Alpha is space angle. With respect to space, if you think of, this is going to be square wave. So let me have this square. Only one single step this is going to be. Anyways, now you please tell me if it is going to be square, which means in each and every square wave will be there or not, right? So the same distribution. Why? Because A conductor proportional to B already we know, which means if my B is single step, that means A conductor has to be single step. So let me consider here. This is going to be time and this is EMF. Let me consider EMF here. Now just see here. First, what is going to happen when this particular rotor, rotor is this way, right? See, rotor is going to be this way. This is north pole, this is south pole, and this is how the MMF is, right? MMF is. This is going to be the MMF. What is going to happen? It is going to rotate in this direction. Now, when this MMF is rotating, first it will encounter A3, right? When this north pole and this south pole, what is going to happen? Firstly, north pole will come to A3, south pole will come to A3 dash. I hope you are understanding my point. What is going to happen? At some time, see, right now EMF is 0, right? Why? Because here if you think of interpolar axis, 0. But if you think of here, see, very simple. This is north pole, this is south pole. When this is rotating this way, first time it is going to influence what? A3 and A3 dash, means that first it is going to influence A3 and A3 dash, which means now since the MMF is going to be square, the induced EMF here is also going to be square, or we can say step, single step. So this is going to be 1 this way. This is going to be A3, let us say. Now what will happen after that? When this north came to A3 and this one A3 dash, after some time it will go to A2 and A2 dash. So after some time, see here, mind my words, initially it was here, it came here. Now after some time it is going to go to A2, means after some angle in space, which means after some angle in time I will get induced EMF of A2. Are you getting my point? Again, see here, in space if you rotate this by some angle here, then what is going to happen? A3 and A3 dash, induced EMF in A3, positive maximum, you will get that. Now what is going to happen after that? Then again if you rotate it like this, further rotate this way, means what? If you are again rotating it in space, if you are rotating the field in space again by some angle, then what is going to happen? In time, after some angle, you are going to get induced voltage, and that induced voltage will also be same as square. Why? Because A conductor is proportional to B. That's it. Very simple concept. Again what will happen? Once this north pole has come here, south pole has come here, after some time, furthermore rotation in anti-clockwise direction, what is going to happen? This north pole will reach A1 and A1 dash, which means after some time in space, means after some space angle, which means after some angle in time also, because space and time are synchronized. So here let me consider yellow. Let me write this as, red was EA2, right? This was EA2. Now let me consider this yellow as EA1, for example. So if it is EA1, what is going to happen? Very important. See, if it is EA1, after some time again in space, after some rotation in space, there is going to be induced EMF in A1, which is going to be maximum, and it will remain maximum for again some time, which means this is going to be delayed again, EA1, furthermore delayed in time. Why? Because delayed in space. First A3 will come maximum, then A2 will come, then A1 will come in space. So similarly in time also, A1 will come, A2 will come, A3 will come. If you think of here in the previous one, what used to happen? At the same time I used to get A1, A2 and A3 maximum. At the same time I used to get A1, A2 and A3 maximum. Whereas now what has happened? Yes, so now if you see here, what used to happen here, if you think of this MMF wave, when it was rotated here this way, means North Pole came here, South Pole came here. There, if you think of what happened, at the same time, at the same instant itself, A1, A2 and A3 became maximum. A1 maximum, A2 maximum, A3 maximum occurred at the same time. So A1 maximum, A2 maximum, A3 maximum occurred at the same time. So addition, we got it here. A1, A2 and A3 in series when we thought of. Now, see here. But here if you see, since A3 maximum occurred first, this blue. After some time, A2 maximum occurred, means red. After some time, yellow. A1 maximum occurred. Now, if I connect A1, A2 and A3 in series, A1, A2 and A3 in series, then what will I get here? Very simple. A1, A2 and A3 in series means what? See here. If I have conductor A1 like this, A1 dash, A2 dash, A3 dash. Back to back connection and then again series. Again back to back connection, again series. See again one more time. A1 back to back connection, A1 dash. Again A2 back to back connection, A2 dash. Again the same wire, A3. So if I do this, then what will I get? I will get addition of this, means voltage is going to be added. Now see here. What will happen here? Let us see. The moment voltage is getting added, let me draw this as A1, A2 and A3. What is going to happen? See, in this particular portion, if you see, blue is there, right? In this particular portion, what you have? You have blue plus red. In this portion, if you see, you have EA3 and EA2 both. So, this is going to be added, EA3 and EA2. Here, if you see, you have EA3, EA2 and EA1 also. See here, you have blue as well, red also, right? Blue, red and all yellow color as well, which means this is going to be furthermore increased this way. After that, what is going to happen? Here you have only two colors, which means it will again come down. Two colors. Again, you have only one color, so this is going to be this way. So here what happened? You got stepped wave. Stepped induced voltage. Now see here, very important. Yes, so here when A1, A2 and A3 were connected in series, we got this one step wave. And now, see here, this happened because I had all the three conductors in the same slot, whereas in the next case if you see, what happened? Here in this case, I got stepped wave like this, which means this is better sinusoid or not? Better sinusoid than the previous. Another observation if you see here, the flux density here is what? Square. So, the same flux density you are going to have here. Meaning that for the same flux density distribution, by distributing the windings, see here, for the same flux density distribution is there, here also square is there, here also square is there. But what happened here? Here you had all the three conductors in the same slot. So you got induced EMF this way. Here if you see, what has happened? EA1, EA2 and EA3 if you think of, you got only one single step for the same flux density. And here also, for the same flux density distribution, you got what? Stepped, which means it is what? Better sinusoid. So sir, it's okay, we have understood about it. We have understood about the advantages of the distribution. Are there any negative points also? Yes. What are those? See here. If you think of RMS value here, RMS value here. What is going to happen? This RMS value will be nothing but 3 times E conductor only. RMS value for this particular is going to be 3 times E conductor only. This one, right? Same, simple. So, this one. But if you see here, what has happened? These pieces which were there in the previous one are not present now, which means RMS value will be reduced, is going to be reduced. Right, see here. Previously, I had this whole block here like this. But here if you see what has happened, these pieces are cut. I hope you are getting the point. So, which means RMS value will be decreased. Now, what is another disadvantage related to this? See, when we say what is going to be there, RMS value is reduced here. Why? Because see here, previously if you have this, you had the one single block here, right? But now what has happened? Some pieces of the blocks are skipped, right? That is the reason if you think of RMS value will be decreased. Now see here, what happens then, sir? Yes, if RMS value has been reduced, what is going to happen, sir? Let us say, for example, alternator. Let me consider one alternator. Right now, this particular alternator is supposed to supply, let us say, 11 kV. Right now, see here. But now, see what will happen is, because of this particular thing, distribution, because of distribution of winding, what is going to happen? I will not get 11 kV. Rather, I may get something around 10 kV or 9 kV. Any value, it can be there. But it has to be less than this one. So, in order to induce this extra voltage, means in order to make it 11 kV, what should I do? I should increase the number of turns. Which means when RMS value is reduced, I have to increase the number of turns. Which means requirement of copper is more. Requirement of copper is increased, which means cost is increased. So, sir, you may say, sir, but see, sir, what has happened here? RMS value and all, stuff like that. So, everything is a disadvantage for us, right? Yes, it is a disadvantage, but the fact is, we love sinusoids. So, even if it is expensive, it's okay. We don't care about it. Why? Because we love sinusoids. We want it to be sinusoid. We want our induced EMF to be sinusoid. Because why? Because we love sinusoid. That is the reason. Anyways, now see here. What is next? Yes, means what? At any cost, I want sinusoid. Even if cost is increased, it's okay. Now, in the immediately next session, we will be discussing about distribution factor. What is distribution factor and all, we will see. What is the importance? Yes. So now, if you observe here, see, what happened? RMS was reduced, because of which number of turns were increased, because of which copper requirement was increased, because of which cost was increased. So, moral of the story is what? Because of distribution, of winding, what happened, sir? Harmonics in induced voltage drastically reduced. but volume of copper requirement has increased. So because of distribution, harmonics, how harmonics are? Yes, 100% harmonics, right? See here, initially we had only one pulse like this, but now what we have now, we have stepped pulse, which means better sinusoid, which means harmonics are reduced. So we can say that because of distribution, what has happened? Harmonics in the induced voltage are reduced, but RMS is also reduced. There is a reason. Volume of copper requirement has also increased, but it's okay, no problem. Anyways, thank you.